હા સર, હવે ચેન્જ થયું. હા હા, સ્ક્રીન શેર જ રાખું છું સર. એકચ્યુઅલમાં છે ને ભૂલથી માટે હું સ્ક્રીન શેર કરી દઉં છું, બરાબર. હા હા, સોરી સર. ઓકે ઓકે સર, કઈ પ્રોબ્લેમ હશે તો હું તમને ખાલી ફોન કરીશ. હા હા, ઓકે, ચલો, થેન્ક. હા હા, મ્યુટ કરી દઉં છું. ઓકે.
Hello. Hello. Can you hear me? Hello.
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 Sir.
Yes, ma'am. Can
Yes,
you?
yes, you are audible.
Okay, fine.
Okay. Okay. So can I start?
Just a minute. Let me check whether I can share the screen or not.
Okay, you can check.
You cannot start screen share while the other participant is sharing.
Okay. That's why I'm stopping my screen.
Okay.
Just yes, sir. Now you can share your screen.
Just a minute. Is it visible, my screen?
Just a minute, sir. Not visible. Just try once again, sir.
Okay, now please check.
There is a one option screen share.
Yes, I have joined. I have clicked on that option.
Okay, just a minute. The screen is not visible, sir.
Okay.
Just a minute. Hello.
Yes, is it visible now?
No, sir. Your screen is not visible.
Okay, let me rejoin again or let me share again.
Okay,
Okay,
sir.
just
You.
a minute. Uh, please check now.
Yes, sir. Yes, sir. Your screen is visible.
Okay, just a minute.
Yes, your screen is visible now. Yes. So very good morning to all. I welcome you, Dr. Deepak Prajapati, sir, on this webinar on behalf of Parul University. I just wanted to give a short introduction of Dr. Deepak Prajapati, and then we will start the webinar. Yes. Dr. Deepak Prajapati is currently working as an assistant professor in government in Gujarat. He has completed his BSc in 2004, MSc in 2006, 2008 from Sardar Patel University. He has completed his PhD from Gujarat University in year 2018, and he is teaching engineering mathematics since 2007. 15-year experience in teaching engineering mathematics, and his research area is the modeling and fluid flow through a porous media. On an average, he has published papers in international as well as the national journal, and recently he book that is a complex variable and a partial differential equation in tech knowledge in 2020. Along with that, he has started his YouTube channel, that is Engineering Mathematics, for providing the free learning, free learning to these engineering, BSc and MSc mathematics, as well as he has 550 YouTube video on his channel. So thank you very much, sir, for joining us in. You can start now, sir.
Okay, thank you, madam, for nice introduction. And I welcome all the participants and respected faculty members in my webinar on harmonic elimination in multi-level inverter using Newton-Raphson method. So in this webinar, we are going to discuss how we can use Newton-Raphson method or how we can use mathematics in the power electronics area of electrical engineering. So we will start our session with the discussion of Newton-Raphson method, and then we will see the brief introduction of multi-level inverter, and then we will discuss how we can eliminate harmonics using Newton-Raphson method. So before going for multi-level inverter, let me explain the concept of this harmonic briefly. So we are already familiar with sinusoidal curve. Suppose this is XY plane, then we know that this type of curve is sinusoidal curve. Now, in the language of power electronics, they consider this type of curve.
जूम से ज्वाइन करना है.
Hello, hello, ma'am. Can you hear me clearly? Hello. Am I audible? Hello. Am I audible to everyone? Hello. Can you hear me, ma'am?
Okay. हाँ, मैं ज्वाइन होगी, वेबिनार स्टार्ट भी हो गया मैम.
हेलो
मैम 7 लोग सर मिला के टोटल 10 है.
हेलो.
यस मैम, खाली बता देना ना, वहाँ जूम पे ज्वाइन करना है. ओके ओके, चलो, थैंक यू मैम.
Hello, ma'am. Can you hear me?
Yes, sir, you are audible.
Okay. So if there is any problem, you can please ask me during the session. If there is some issue related to network problem or any other thing, then please inform me.
Okay, sir, definitely.
Okay, fine. So dear participants, I was discussing about this type of sinusoidal waveform. We are familiar with this type of curve. It is the graph of sine theta, and in the language of electrical engineering, they call this type of waveform as sinusoidal waveform. So this type of waveform is observed in the alternating current, that is in the alternating current which we are using in our electrical systems. So this is the ideal form of alternating current, but we will see that in some electrical systems it is not the case that output voltage is always alternating current. It contains some disturbances which are known as harmonics. For example, if we denote this by, suppose this is fundamental sinusoidal waveform which has the representation sine omega t, then this is the expected output voltage waveform. But due to some issues in the electrical systems or due to some switching actions that we will discuss later, we are having some other combinations of waveforms. We may have this type of disturbances with this ideal sinusoidal waveform. So if we consider this, then this is also sinusoidal waveform, but it is having this type of equation sine 3 omega t, because if you observe, it completes 3 cycles here. Similarly, we may have other waveforms with this ideal waveform. So all these extra voltage waveforms are known as harmonics. And due to presence of these harmonics, we are having many problems in the electrical systems. They may damage the electrical system, and some problems related to overheating are also observed. So our aim in this lecture is how to remove this type of harmonics. So we will see that how harmonics are generated and how to remove harmonics using Newton-Raphson method. So for that, first we are just taking brief review of Newton-Raphson method. Now we are familiar with the Newton-Raphson method for solving non-linear equation, say fx equal to 0. If fx is a non-linear function, then this is called non-linear equation. And we know Newton-Raphson method for solving this single non-linear equation. So we know that if x0 is the initial guess to the exact solution, suppose x0 is the initial guess to the exact solution, then first approximation is given by x1 equal to x0 minus value of function f at x0 divided by first derivative at point x0, provided that first order derivative exists and it is non-zero. So this is the Newton-Raphson iterative scheme for single nonlinear equation, and we can generalize this. Instead of x0, we can use this general formula. Suppose I am interested in the m plus 1th approximation, then this is equal to xm minus value of function f at xm divided by first order derivative at xm, and m takes the values 0, 1, 2, and so on. Now the convergence of this Newton-Raphson method depends strongly on the initial guess. If initial guess is selected in such a way that this sequence of approximations will approach to the exact solution, then only we will get the convergence. Now we are not going to use this Newton-Raphson method for single equation. In this webinar, we will require Newton-Raphson scheme for solving n non-linear equations in n variables. Suppose first non-linear equation is function f1 of n variables, say x1, x2, xn equal to 0. Another function denoted by f2, say f2 of x1, x2, xn equal to 0, and so on. So suppose I have system of n non-linear equations in n variables, say x1, x2, xn. Then I want to generalize this Newton-Raphson iterative scheme for solving these n non-linear equations. So for that, we will use this similar formula, but instead of this single variable, now we have n variables, so we will use vector notation. Here I will write x bar m plus 1 equal to xm bar equal to value of function at xm bar, and instead of this first order derivative, we are going to write Jacobian of the function f at point or at vector xm bar. So first we will see what is this function f. So function f is the vector function whose components are these n functions f1, f2, fn. If we take the transpose, then this is our f. And we know the definition of Jacobian. This I can rewrite as, if we write as a column vector, it can be written in this way. And we know how to find out Jacobian of this function at point xm bar, where xm bar is also a vector having n variables x1, x2 up to xn. So by the definition of Jacobian, because we are having n component functions, first row of the Jacobian will be partial derivatives of first function, say f1, with respect to x1, x2, and xn. This is the first row of the Jacobian. Similarly, second row will be partial derivatives of function f2 with respect to x1, x2, and xn. And because we are having n functions, last row will be partial derivatives of function fn with respect to x1, x2, and xn. Now here in this formula, we will replace this by Jacobian. But here we cannot write that f of xm bar divided by this. Instead of this, we will write in this way, vector xm bar minus inverse of the Jacobian matrix. Here I am writing inverse of the Jacobian matrix times value of function at xm bar. So for system of n non-linear equations, this will be the our iterative formula for Newton-Raphson method. Xm plus 1 bar equal to xm bar minus Jacobian of function f at vector xm bar and its inverse multiplied with value of function f at xm bar. So we will remember this iterative scheme. Now suppose I want to use Newton-Raphson method for solving this system, then again I have to start with the initial guess that we will denote by x0 bar, and we will assume some initial solution. Suppose x0 bar is say x01, x02 and x0n. Then our first iteration will be denoted by x1 bar, and it is given by x0 bar minus Jacobian of the function at this vector x0 bar and its inverse times value of function f at x0 bar. So using this formula, we will obtain first iteration. Now here, this I can rewrite this as x0 bar plus h0 bar, where this h0 bar is nothing but this negative of Jacobian matrix, negative of inverse of Jacobian matrix multiplied by value of function at x0 bar. And if we multiply this equation by Jacobian of f on left hand side, then we will have Jacobian of f at x0 bar times h0 bar equal to minus f times x0 bar. So this will be a system of n linear equations. This is going to be a linear system, and we can solve this linear system easily either by Cramer's rule or Gauss elimination method. And we will assume that this h0 bar is having n components, say h1, h2 up to hn. So we can find out this h0 bar, which we will call as displacement vector. This h0 bar will be known as displacement vector, and this displacement vector will be obtained by solving this linear system with respect to h1, h2 and hn, n variables. And using this solution, we will obtain first iteration x1 bar equal to x0 bar plus h0 bar. Then we will check whether f of x1 bar is 0 or not. If it is non-zero, then we have to go for second iteration using this x1 bar. So formula for second iteration will be x2 bar equal to x1 bar plus h1 bar, where this h1 bar is the solution of this system. Jacobian of f at x1 bar times h1 bar equal to minus value of f at x1 bar. So we will solve this system and we will obtain h1 bar, and in this way we will proceed further, and we will continue this process until desired accuracy, or until we obtain the two solutions which are correct or which are nearly equal up to some decimal places. So I hope I have explained this Newton-Raphson scheme for solving non-linear equations. So all we have to do is we have to start with the initial guess, and then we have to obtain the value of function f at initial vector or initial guess, and Jacobian at that initial vector, and we will solve this type of system to obtain h0 bar. Then we will obtain x1 bar. So in general, I can write that this Newton-Raphson scheme for solving nonlinear systems is x m plus 1 bar equal to xm bar plus hm bar, where this hm bar can be obtained by solving the linear system Jacobian of f at point at vector xm bar times hm bar equal to minus value of function f at xm bar. So every time we have to calculate value of function at xm bar and Jacobian at xm bar, and we will obtain this system, linear system, and that we can solve easily using Gauss elimination method. So this is the idea of Newton-Raphson method. So that I have briefly written here. Just a minute. So I am not going through all these sides, but I am not discussing that how we can develop Newton-Raphson method. So Newton-Raphson method for n linear equations can be developed using Taylor series expansion, but due to lack of time, I have not discussed the development of the Newton's method. But as I discuss, this is the Newton-Raphson method for solving non-linear system in n non-linear equations and n variables. Here number of equations and number of unknowns must be same because we are having this Jacobian matrix, and we require its inverse. So inverse of matrix is possible only if it is a square matrix. So this condition is required, or we can say that it is the limitation of the method. If number of equations and number of unknowns are not same, we cannot use this method. So we will remember this formula where this hm is called displacement vector, and it is the solution of this linear system Jacobian of f at xm bar times hm bar equal to minus fm minus value of f at xm bar. So this is what I have explained Newton-Raphson method for solving non-linear equations. First requirement is appropriate initial vector x0 bar, and then until convergence we have to obtain these vectors x1 bar, x2 bar, x3 bar, and so on. We have to compute Jacobian matrix at every vector x1 bar, x2 bar, x3 bar, and we have to solve the linear system. This J is the notation for this Jacobian, and in this linear system Jacobian is known to us. This is also known to us. Unknown quantity is this vector hm bar, and once we obtain this vector hm bar after solving this system, we can obtain next iteration using this. So this is all about Newton-Raphson scheme for solving non-linear system, of course in n variables and n equations. Now we discuss what is meaning of inverter. Just a minute. So inverter is an electrical device or electrical circuit which converts direct current, that is DC current, into alternating current. We can understand in this way. Suppose this is inverter, then here input is DC current, and inverter converts DC current into alternating current having sinusoidal waveform. So the function of an inverter is to change a DC input voltage to a symmetric AC output voltage of desired magnitude and frequency. Now the output voltage waveforms of ideal inverters should be sinusoidal. It is expected that inverter must give the output voltage as sinusoidal waveform. But in practical situation, this is not always possible, or it is impossible in practical situation. The output of inverter may be distorted sine wave like this. Okay, you cannot always have, or you cannot have this type of ideal sinusoidal wave as the output voltage. Okay, but you may have this type of distorted sine wave. So this is ideal sine wave, and we are having some distortion here. So this is known as, distorted sine wave. So due to this type of distortion, we may have some issues like overheating or damage of electrical system. So this is not expected output voltage. Now, how to gain the expected output voltage? So as I have discussed that this output voltage contains harmonics. So if we can remove those harmonics, then we can have the output voltage as approximately sinusoidal. So multi-level inverter is the electrical device which helps us to obtain this type of approximately sinusoidal waveform. So that we are going to discuss. So as I discussed, the waveforms of practical inverters are non-sinusoidal and contain some harmonics. So for low and medium power applications, square wave or quasi-square wave voltages may be acceptable, but for high power applications, low distorted sinusoidal waveforms are required. Square wave means this type of waveform is allowed. Sometimes they allow this type of waveforms also. So these are allowed for low and medium power applications. But for high power applications, we require very low distortion. So this is the figure explaining harmonics, which I explained at the beginning of the lecture. This red color is the ideal sinusoidal wave. This white color denotes the third harmonic, which we can write as sine 3 omega t. This blue color is the fifth harmonic, sine 5 omega t, and the seventh harmonic is this one, sine 7 omega t. So why I am calling this white waveform as third harmonic? So you can observe that it completes 3 cycles. This one cycle, another cycle, and then this one. So that is the reason why it is known as third harmonic. Similarly, this fifth harmonic, you can see this is one cycle, second, third, fourth, and fifth. So it contains 5 cycles to complete up to this. So that is the reason why it is known as fifth harmonic. And the resultant output waveform is denoted by this yellow color. This is the resultant. So this resultant is obtained by adding these waveforms. This is fundamental, that is ideal, plus if I add all these waveforms, sine omega t plus sine 3 omega t plus sine 5 omega t and sine 7 omega t, then I will obtain this yellow output voltage waveform. So that is the resultant, and we can see this resultant is obtained by adding this third harmonic, fifth harmonic, seventh harmonic, and fundamental component, that is ideal sinusoidal waveform. So because this resultant contains all these harmonics, it is not expected. So we want to remove this harmonics, sine 3 omega t, sine 5 omega t, sine 7 omega t, and so on. Now if we observe this third harmonic, then magnitude of third harmonic is higher as compared to fifth harmonic, and magnitude of fifth harmonic is higher as compared to seventh harmonic. So as we proceed, as we increase the order of harmonics, magnitude of voltage is decreasing. So the only harmonics which are creating issues are of third and sometimes fifth harmonic. Harmonics of order greater than 5 are not creating any more issues, or because they are having their output voltage or magnitude of output voltage is very low in higher order harmonics. There is no problem if they are present in the output voltage current. So we will focus on removing third and fifth harmonics. So that is our aim in the subsequent part of this webinar. Okay, so now we briefly discuss what is multi-level inverter. So for that, just a minute, I will require another page. Suppose my output voltage waveform is like this. Okay, I am trying to explain multiple levels of voltages, and this similar waveform is repeated here also in negative half cycle. And suppose here we consider angles, and here we consider function f, and this is function of omega t. Here we start with 0. Suppose this is theta 1 at this point, theta 2, and so on. So if this value is say VDC by 3, then because these two are equal in magnitude, this is going to be 2 VDC by 3, and this is going to be 3 VDC by 3, that is VDC. And here we will have negative of this, minus VDC by 3, minus 2 VDC by 3, and minus VDC. So you can count the different levels. Here value of voltage is 0. Here value of voltage is VDC by 3. Here value of voltage is 2 times VDC by 3, and here it is 3 times VDC by 3, that is VDC. So we can count. Similarly, here also we have this different levels. So this type of output voltage is generated in multi-level inverter. The output of multi-level inverter will always be having more than one voltage levels, and we are going to expand this as a Fourier series in the remaining part. So multi-level inverter is an electrical circuit which is having multi-level output voltage waveform. So what is the need of multi-level inverters? So multi-level inverters give us high output power from medium voltage sources like batteries, supercapacitors, etc. And I am not going to discuss these types of multi-level inverter. We will only focus on cascaded H-bridge multi-level inverter. So due to lack of time, I skip all those slides. Now I will again briefly go through this figure, multi-level inverter. So multi-level inverter consists of 3 cells. We call this as cell number 1, or first cell, that is denoted by H1, then H2 and H3. And there are separate DC voltage sources at each cell. Another name for cell is H bridge. So I am having 3 H bridges here, and I am having 4 switches in each H bridge. Now output voltage will be generated by the action of diagonal switches. That is, if I consider S1 and S4 turn on, then I will get some output voltage. And similarly, if I turn on S2 and S3, then I will get output voltage. If I turn on S1 and S2 simultaneously, output voltage will be 0. And if I turn on S3 and S4 simultaneously, output voltage will be 0. And I cannot turn on S1 and S3 because that is going to damage my circuit or my device. Similarly, I cannot turn on S2 and S4. Now from each H bridge, we will have some output voltage. So output voltage from H1 bridge is denoted by VDC1, and here we assume that all the output voltages are equal, and that equal value we consider as VDC by 3. Now because I am having 3 H cells or 3 H bridges, I will get 7 levels of output voltage waveform. So the formula for levels in the output voltage waveform is 2 into m plus 1. So here I am having 3 H cells or 3 separate DC sources. I will have 2 into 3 plus 1, that is 7 voltage levels in the output generated by this multi-level inverter. So here I have shown this output voltage waveform of this multi-level inverter. So you can see on x-axis I am taking values of theta, that is omega t, and on y-axis I am considering output voltage, and we will consider output voltage as the function denoted by V0 of omega t or V0 of theta. Now here we observe one thing, that this theta 1, theta 2, theta 3 are the angles, and these angles are known as switching angles. Now these switching angles are the moment of change in output voltage level. That is, at theta 1 we can see output voltage is changing. Similarly at theta 2, here output voltage is changing from VDC by 3 to 2VDC by 3. So our aim is to decide the values of these switching angles such that this output voltage waveform cannot contain third and fifth harmonics. So how to eliminate third and fifth harmonics, and in such a way that this output voltage waveform will be approximately sinusoidal. So for that we are going to use Fourier series expansion. If we observe, then this output voltage waveform will always be periodic with period 2 pi. It is starting from theta equal to 0 and going up to 2 pi. And remember that the output voltage waveform generated by this multi-level inverter, cascaded H-bridge multi-level inverter, will always be periodic. That is, in the another length of 2 pi, this voltage waveform will be repeated. So the graph of voltage waveform in every interval of length 2 pi is same. So we will do analysis in this interval 0 to 2 pi. Now if you observe that at this point angle is pi by 2, here we have pi, and this is periodic function, so we can express this periodic function in terms of Fourier series. We know that every periodic function can be written as a Fourier series expansion. Now our function output voltage is denoted by V0, and if we write it as a Fourier series, we will have A0 plus sigma an times cos n omega t, n is taking 1 to infinity, plus sigma bn sin n omega t, n is from 1 to infinity. Again, if we observe that this periodic function is odd function, okay, that means we can check that f of minus theta will be equal to minus f of theta for every value of theta. So because this is odd function, we can say that this A0 and An will be 0. So this output voltage waveform will not contain these cosine terms. Another observation is this function is quarter symmetric, or we are having quarter symmetry here, that we can observe in this way. If we take partition here, and you can see, you will observe this same portion in all the remaining parts up to this, and then up to this, and up to this. So this is quarter wave symmetry. I am not discussing its definition, but it is very easy to understand the quarter wave symmetry. So if we have quarter wave symmetry and plus odd function, then this Bn will be 0 for all even values of n. If we consider n is even integer, for even values of n, Bn will be 0. Due to lack of time, I am not discussing all these things. I am just giving you the idea that because of odd and quarter wave symmetry, we will not have an and a0 in the Fourier series expansion. Also, Bn will be 0 if n is even. So the only contribution will be this part. Our output voltage waveform will contain only this series for odd values of n. That is, this we can write as B1 sin omega t plus B3 sin 3 omega t plus B5 sin 5 omega t, and so on. So this first function sin omega t is fundamental sinusoidal curve. This sin 3 omega t is third harmonic, and this sin 5 omega t is fifth harmonic. And formula for Bn will be, if we observe here, to find out Bn, we have to integrate from 0 to 2 pi. The usual formula is integral from 0 to 2 pi f of omega t sin n omega t dt. Instead of f omega t, we have v0 omega t. But we can observe that due to quarter wave symmetry, this we can write as 4 times integral from 0 to pi by 2. So I have used that formula to obtain the values of these Bn's, and that is for n equal to 135 and so on. And instead of omega t, for convenience, I am using theta. So I will have Bn equal to 4 by pi 0 to pi by 2 v0 theta sin n theta d theta. And after integration, we will obtain. Now here we can again observe that this is we are having our v0 different values up to 0 to theta 1, v0 is 0. Then in theta 1 to theta 2, v0 is vdc by 3. In theta 2 to theta 3, v0 is 2 vdc by 3. And in theta 3 to pi by 2, v0 is having vdc. So that we have to separate, or we have to break our integral into these parts. In 0 to theta 1, v0 is 0, that I have not written. And after integration, we will obtain this Bn equal to this formula. And because n is odd here, and we know that cos n pi by 2 is 0 if n is odd. We know that cos pi by 2, cos 3 pi by 2, all are 0. So this is the formula for Bn. And if we substitute this in the Fourier series, this will be the Fourier series for output voltage generated by multi-level inverter. Now here our aim is to remove this third and fifth harmonics. This I can write as B1 sin omega t plus B3 sin 3 omega t and B5 sin 5 omega t, and so on. So if I want to remove third harmonic, I have to take B3 and B5 equal to 0. And I require this fundamental component. And suppose my desired voltage, if I am interested in the ideal sinusoidal waveform. So suppose I assume that magnitude of this output voltage required is V1, then I require this V0 omega approximately as V1 sin omega t. So if I compare both sides, I have to consider B1 equal to V1, and I want to remove third and fifth harmonic. So I will take B3 and B5 equal to 0. So using this logic, we obtain these formulas. B1 equal to V1, and B1 is nothing but this is the formula for Bn. For n equal to 1, we will obtain B1 equal to 4 VDC by 3 pi cos theta 1 plus cos theta 2 plus cos theta 3. Similarly, for n equal to 3, we will obtain cos 3 theta 1 plus cos 3 theta 2 plus cos 3 theta 3 equal to 0. So now we consider one more thing, which is known as modulation index. So this modulation index is defined as the ratio of the fundamental voltage V1 to the maximum value of V1. Now here V1 is given by this formula. So V1 will be maximum when we have all the angles equal to 0, because maximum value of cosine function is 1. So if we take all the angles equal to 0, then maximum value of V1 will be 4 VDC by 3 and 1 plus 1 plus 1, that is 3, here pi. So maximum obtainable value of V is 4 VDC divided by pi. And this modulation index is defined as the ratio of the fundamental voltage V1 to the maximum obtainable voltage V1 maximum, that is 4 VDC by pi. We obtain that maximum value of V1 is this. So this is the modulation index, and I use that formula here so that I will obtain this equation. Cos theta 1 plus cos theta 2 plus cos theta 3 equal to 3 times modulation index. Now I take this on the left hand side, and we can observe that this is the system of 3 non-linear equations in 3 variables, theta 1, theta 2 and theta 3. And to solve this system, we are going to use Newton-Raphson method. So we require values of theta 1, theta 2, theta 3 such that all these equations are satisfied. So as I discussed, I will require this formula theta m plus 1 bar equal to theta m bar plus vector hm bar, where vector hm bar is the solution to the linear system dfm Jacobian at theta m bar times hm bar equal to value of function f at theta bar. So our function f will be function having these 3 functions as its components. So I have taken f of theta equal to this, and I can compute the Jacobian matrix for this. So this is first function, say denoted by f1. So in the first row, we have written derivatives of this function. Second row contains derivatives of this function with respect to theta 1, theta 2, theta 3, and third row contains derivatives of this function with respect to theta 1, theta 2, and theta 3. And I am considering initial guess as theta 0 equal to this. So first I have to compute these two, value of function at theta 0 and Jacobian matrix at theta 0. And solving this system, I will obtain first displacement vector h1 bar. So I have computed this here. Okay, you can see here Jacobian matrix at this vector. For that, I am taking theta 1 equal to 9, theta 2 equal to 28, theta 3 equal to 55 in this, and this is also computed. And then I solve that system. This is Jacobian matrix times displacement vector equal to minus f of theta bar, and this we have solved by Gauss elimination method, and we obtain this first displacement vector. So using this, we obtain the first approximation, theta 1 equal to theta 0 bar plus h0 bar. And then we will require theta 2 bar. So for that, formula will be theta 1 bar plus h1 bar, where h1 bar is the solution of the linear system, which will use now this theta 1 bar. So then we solve this system, minus f of theta 1 bar, and we obtain H1 bar after solving this system, and we will obtain second iteration. So continuing in this way, I have obtained this solution. After 9 iterations, I am getting this solution correct up to 2 decimal places. And this solution corresponds to the modulation index MA. So if we consider these angles theta 1, theta 2, and theta 3, which we have obtained, if we operate switches in multi-level inverters such that at those values of theta 1 and theta 3, this output voltage level are changing, then third and fifth harmonics will be eliminated. So the conclusion is if the inverter output is symmetrically switched during the positive high cycle of the fundamental voltage to VDC by 3 at this value of theta 1, then at this value of theta 2, it is changed to 2 VDC by 3, and at this value of theta 3, it is changed to VDC. And similarly for negative cycle, then the output voltage cannot contain the third and fifth harmonics. So in this way, we can eliminate third and fifth harmonics, which are creating issues in the output voltage waveform. We are not worried about the higher order harmonics because magnitude of voltage for those harmonics is not very high. It is very small, so it is not required to eliminate higher order harmonics. So in this webinar, I have shown you how to remove harmonics in the output voltage waveform generated by multi-level inverter, and to remove those harmonics, we have used Newton-Raphson method for solving non-linear systems. So I think I have no much time, and I conclude my webinar here. And if you have any questions, we are having 10 to 12 minutes, so we can discuss. Thank you, madam. Thank you all the participants and respected faculties.
Thank you very much, sir, for the such a nice webinar. Participant, if you have any, can ask, because we are having 10 minutes. Anybody? If so, I can unmute participants. Anybody? Yes, sir. I think you have explained your topic very nicely. I think nobody have any query, but I am having one query, sir.
Yes,
Can you modulation index? What is the importance of modulation index in this particular solution?
Okay, I have not gone through the purely electrical aspect, but
Yeah.
They are not, I think they are not comfortable with this much big expression. Let me go to that slide. Just a minute.
No issue, sir. You can take your time because we are having 10 minutes.
Okay, so they are using modulation index to write down this equation. See, our aim is to obtain the output voltage waveform as sinusoidal, but that output voltage waveform generated is not sinusoidal, it is containing some harmonics. So before doing this analysis, we have to first make the target that how much peak value is required in our our expected output voltage. So they assume that suppose peak value required is V1. Now, so this is the peak value required. And after doing this analysis, they from this expression, they obtain that peak value required is given by this expression cos theta 1 plus cos theta 2 and so on. So they find out the maximum value of this desired output voltage, and they divide this required output voltage by its maximum output voltage, and they call this as modulation index. So I think the only purpose is to make this quantity as dimensionless variable. If we divide this v1 by its maximum value, then it will become dimensionless. So that is the only purpose I have observed, but I am not the expert of power electronics, so that is the only thing which I observe here. But this is very nice question.
Sorry, sir. I know that you are the person from mathematics.
Okay.
You have nicely explained the whole topic of webinar. You have nicely integrated the different topic of as well as electrical engineering as well as the physics, because this webinar is very much useful for mathematics. Use the Newton-Raphson method as well as the Fourier series, and along with that, you have topics of the power electronic side, or you can say electrical background. So very much you have presented your webinar or your particular topic in such a nice manner. Thank you very much, sir.
Okay, thank you, madam.
Yes, sir. Thank you, sir. If sir, now you can leave the webinar, no issue.
Okay, thank you, madam. Thank you all the participants and respected faculties.
Once again, I wanted to thank Prajapati sir on behalf of Parul University Parivar.
Thank you, madam.
Thank you, sir. Thank you. Bye, sir. All participants, the webinar is over. Thank you very much once again.